All right, so yeah, thank you all for coming to my talk, and I hope you're as enthusiastic about on-demand logistics as I am. So we're going to be talking today about solving optimization models for on-demand delivery using Python OR tools and some DecisionOps tooling that will sort of be in the background making things work a little bit. If you want to follow along, this talk, all the materials for it are on that GitHub URL right down at the bottom here. So you can just go to github.com/Ryan J. O'Neill. That's my GitHub username /2023 Python or PyData Global order up. And you can find all of the code that I'm going to run in there. You can also just look at it afterward. But anything that I'm doing here, you should be able to maybe hopefully follow along with. All right. So again, my name is Ryan. I'm CTO and co-founder of Nextmove. I spent the last bunch of years now working in on-demand logistics. My background is in operations research, and before that, I was a software engineer for a while. I think I've been using Python about 17 years off and on now, and been really excited to see sort of how the adoption of data science in Python has exploded over the last many years, and also how that is really moving into optimization. Python is becoming sort of the de facto language for a lot of optimization modeling. And so that's what we're going to be looking at today with these specific applications. So if you're coming to this talk, sorry, I'm having a little bit of a lag with the slides, so just bear with me on that a little bit during the talk. Anyway, you probably have one of two interests. One is you are going to start working on some of these models. You need to maybe do some scheduling or some forecasting or some routing or similar things like maybe order fulfillment or assignment or resource allocation. And maybe you don't quite know where to start, or you want to sort of understand how these things play together in an on-demand logistics setting. So those are really the couple of audiences that this talk is geared at. The things that you're going to come away from it with are a sense of how sort of the three, what I think of as minimum viable models of on-demand work together and what they are, and how you can model them using a single tool. In this case, we're going to use OR tools because it applies nicely to all of these things. There are lots of other things that you could use. And how to sort of work together with these things. So that's what you'll come away with. I'm using a single tool here because, in my opinion, an optimization solver and modeling library is really the most important part of your stack if you're doing decision modeling. I think of it like a Swiss Army knife. And so one of the things I like about giving this particular kind of a talk is that we're going to be using that same technology and same library in three very different ways. And the first way is forecasting, which is not something you typically see an optimization solver used for. It's not the only way to do forecasting, obviously, but it is how we're going to do it here. So if you just had a single hammer that you needed to reach for, an optimization library, an optimization solver is one that you could be quite successful with. And so we should all pick them up. For the example today, we're going to pretend that we are part of what we call the Farm Share Company. We are a consumer delivery service. We deliver carrots and beets and lettuces to vegetable-oriented people. And we're moving from, say, manual siloed processes where we're using a lot of spreadsheets, or maybe we've got like a monopoly board or a risk board, and we're sort of moving pieces around to figure out how to run our operations. And we want to move to some sort of a technology platform and have tighter integration between these things. So the three primary things that we have to do are we need to forecast demand for carrots, we need to schedule our carrot delivery vehicles, and we need to do route planning for our carrots to get them to the actual end carrot consumers. For any one of these things, there's different cadences we could do these at. We'll just sort of assume that we forecast maybe once a month, once a week, something like that, and we schedule sort of in tandem with the forecast to figure out how many drivers we need at each block, given driver availability. And we might route plan daily, but you could take any of these things and extend them to different cadences. It just changes how you think about the model and how you use it. All right, so we've got these three different models. How are we going to solve them? Like I mentioned earlier, we are going to use OR tools for all of these, but within OR tools, and part of the reason that it is interesting to us is that it is a multi-paradigm library. It is a hybrid solver and a multi-paradigm library. It supports linear programming, mixed integer programming, or if you're under 40, it might be linear optimization and mixed integer optimization. It also supports constraint programming, satisfiability, and local search. So we'll use all of those things today. And what we're going to use for our forecasting is actually what's called LAD, or least absolute deviations regression, which is a linear programming model. And for our shift scheduling, we're going to use mixed integer programming or mixed integer optimization. OR Tools also comes with its own scheduling interface, which you could use as well. And I put that in the exercises at the end. And then we're going to use OR Tools' default routing solver, which is based on their constraint programming and satisfiability and local search technology. And again, you could also use something like mixed integer programming, or you could use a commercial option like NextRoute from NextMove or something like that for the routing. So in a production environment, this is how these three things typically work together. We typically forecast some sort of demand, and that produces targets. That combined with targets produces an actual scheduling targets that we need to hit. So for example, our forecast might tell us we're going to have 50 deliveries to do during 2 and 4 p.m. on Friday. And then what we want to do from that is say, given the amount of demand that I have and available drivers and my economic targets, which is essentially orders per driver or orders per driver hour, how can I optimally schedule to be right where I want to be? I don't want to have too many drivers because that's expensive, and I don't want to have too few drivers because that gives bad service. So that's what we do with scheduling. Once we actually have drivers on the ground, or maybe the day before or the week before, depending on how we run our operations, we also need to come up with routes. And the question was just, can I repost the link here? And yes, I absolutely can. So just give me a second to do that. And hopefully this comes up in the chat. This is my first time using AirMeet. So you can follow along there, and that has the requirements.txt. You only need the one module, which is OR Tools. All right. And so the routing model there is what will allow us to say, what sequence do I put different stops in? Where do I go first, second, third, and who is doing those actual routes? So it's really an assignment and sequencing problem is what vehicle routing is. So we'll start for each of these models. What we'll do, and again, this is going to be a little quick, but what we'll do is we'll just go briefly through the structure of the model, which might include some math, it might include some business operational things, and then we'll look at it in an actual script, which is what you'll find in the GitHub. So first, let's look at our forecasting model. I have generated synthetic data, which you can find in the GitHub. It's under forecastinput.json. And what it is sort of data that I think is representative of stuff that we see in on-demand delivery. And so this is daily data broken out by mealtime. And so mealtime is essentially morning, midday, evening, and night, 4-hour blocks. And what we can see here, and again, I've generated this data, so I know exactly what it is, but it's very spiky along the course of the week. So Monday and Tuesday are different from Saturday and Sunday. And it's very different from mealtime. And there are some seasonality trends in here. There's also an overall daily trend. It's increasing in volume. And so it would be fairly normal of us to get data like this from operations and then say, give a forecast that sort of looks into the future to help me figure out what's going on. And we might look at this and say, like, gosh, I don't know. Is there a trend? It looks like there's a trend. What's the trend? I don't know. If we look a little bit more recently, so this would be the last 28 days, and you can see here I generated the data on November 14, so it's a little dated already. This is split out by mealtime again, and there's looks to be some overall trends, but it's a little hard to sort of separate out exactly what's going on. And so we're going to use lab regression against this to try and sort of tease out the variance that is explained by each of the different features that we look at and project into the future a few weeks. So why lab regression? There's a couple of reasons. One is that it's robust to outliers, and so it's a regression that I think is underused. And so here we have sort of a demonstration of what that means. Let's say we've got this curve is our actual predicted, this is our fitted line, and these blue dots are our actuals. What we can see here is that this dot is one unit away from the prediction, and this other dot here is 2 units away. Traditionally, if we're using something like least squares, this purple will be squared and therefore has a much bigger impact on the fit of the model than this single orange bar. And so what this means is that least squares is actually less robust than something like lag regression to outliers. The outliers in the data can impact the fit of the model much more. They have an outsized impact on the coefficients that the model gives us back. So that's one reason that LAD is a nice type of regression. It's also customizable in interesting ways. So if you're using an optimization solver to actually do your forecasting, you can do things. Yes, LAD is equivalent to L1 norm. That's exactly correct. Yep. You're just essentially, instead of squaring these lines, you're just summing them up. It's like how far away is it? And so if we're actually building our regression model using an optimization solver, we can customize that model in any way that we want, right? And so I might be able to do interesting things like do epsilon and sensitivity, right? And stuff like that, which is actually really hard to do with a pre-formulated solver. All right, and another is we can model as a linear program, which is convenient for the talk today because we're using OR tools to solve all of these things. So let's look a little bit at what the model looks like. So if we're coming to regression from an optimization perspective, this is what that model looks like. We're trying to minimize essentially the sum of a bunch of residuals. And those residuals are just applied, they have some norm applied to them, which could be sort of any valid norm. Now, typically, in least squares, that's the L2 norm. But in LAD, all we're doing is we're saying we're going to replace that with the L1 norm. Other than that, it's the same model. Where it gets interesting is if we now split that out, what we can see here is this is the way the least squares model works on the left. And there's a nice closed form analytical solution to that particular model. I can just plug the inputs into an equation, get an output. And I theorize that this is probably why we actually all grew up using least squares, because it's just very easy to implement. I don't actually have to use an algorithm to implement it. I can just use a least squares equation, essentially. If we then go to the right instead and look at LAD regression, what that really becomes is just this absolute value, right, this L1 norm. And that turns into a model which looks like what is below. Essentially, we're trying to minimize the sum of these residuals where it's the absolute value. And so we have to introduce these other variables, which we call Z, to do that absolute value part. And this is what turns it into a linear program. And now we have to use linear programming or linear optimization to solve it. And so I think this might be part of why it has less adoption in general. But we're gonna do it anyway. So I showed you the data a little bit ago. On the right is a Dolly impression of a bunny solving LAD regression, which I thought was interesting. There's nothing particularly new in this implementation. I just stole it from a paper by Rob Vanderby. The slides are in the GitHub, so you can find that link there if you're interested in the paper. It's pretty cool. And so basically doing exactly what he's doing. And again, I designed the data so I know what the features are, and they are an offset, a daily trend, seasonality, solar cycle, and a weekly trend. So we're just going to plug that right into the model and see what happens. All right, so let's do our forecasting speed run. Hopefully we're doing okay on time. All right, so first let's look at what our data looks like. This is, again, generated data. And I just have created JSON where every 4-hour block during a time frame, it has a demand, and it's morning, midday, evening, or night, and that's what our input looks like. Again, that's in the GitHub. You can play with that if you want. In the forecast repo or forecast directory, there's also main.py, which has the OR tools model in it, and the important parts of it are here, where what we're doing is essentially creating a variable for each observation, which is the fitted value, and then a variable for that absolute value, right? And so let me go up here again. Here we go. So this is a continuous variable, which is the fitted value that the optimizer is going to produce. And then the actual residual is another continuous variable, which has a minimum of 0. And so if you remember from the previous slide, what we did was we said, we're going to have AX minus B for each one of these things. And I want to take the absolute value of that. And it requires another continuous variable. And then what we add are constraints where we say that residual has to be greater than or equal to either the actual minus the fitted or the fitted minus the actual. And this is the whole purpose here. This is everything. This is the whole reason it's a linear program. Everything else is just, constructing the data for that. So it's really just sort of data munging. We minimize the sum of the residuals. We call solve and OR tools. We are using, in this case, the skip optimizer, but you could plug in a different linear programming solver here, and it would work pretty well. And then we just pull the data out. And that's really it. So when we run it, let me go into our forecast. What I'm going to do is just push that into next move and run it there. And so now it's pushed into a remote environment. And I'm going to run it remotely with that input.json. And it'll just give me back in a few seconds a forecast, which we can look at. Okay, and so here what we have is another JSON blob that it gave me back. And if I go up far enough, I can see, way back when, that there will be demand. So this is observed demand data for a particular day and block, and then forecasted demand, right? And so what we're expecting is that not to exactly match, so that's good. And then if I go down to the bottom, I can see that I have forecasted into the future from when the model was run, which was based on data from November 14. All right, so that's my forecast. Let me now go back to our slides. So if I plot this, this is the output that I get. And it's interesting because, given that I designed the data, I know exactly what the best model is. So this is really the best we should be able to do. And so we can see here we're going along. We've split this out by mealtime, and then we're forecasting to the future. So the orange are the actuals, and the bars are the residuals. And we can see we have this forecast going forward, and we used OR tools to do it. All well and good. All right. So now that we have our forecast data, the next question is, how do we schedule? So let's look at our scheduling model. So there's two inputs to scheduling. One is targets. And so these are economic targets that we set as the operator, and the other is availability of our drivers. And so when we're setting economic targets, it's fairly typical to sort of understaff during low volume periods, so you can maintain service levels, to overstaff, and to try and essentially make more money during high volume. Higher volume leads to less variability, means you can be more efficient, and so on and so forth. So what I've arbitrarily done is said, I want 3 orders per driver hour during morning and night, 4 during midday, and 5 at evening. And so that's given my operations, I think that'll be a pretty good sort of target to meet. And our objective for scheduling in this case is just going to be minimizing some penalty of overstaffing and understaffing. And those can and probably are typically different penalties. You might want to overstaff, for example, on the day after Thanksgiving when you need to do a lot of deliveries. Or you might want to understaff during other certain times, depending on sort of how your economic conditions or your business is going, and so on and so forth. All right, so this is the scheduling model that we're going to look at, and this, if you look at it, is a mixed integer program, or has binary variables. And just briefly going through the math of it, we're going to minimize the penalties of oversupplying and undersupplying for every hour that we are oversupplied or undersupplied in the output of the scheduling model. And then what we're going to do is we're going to add a constraint, which is that the supply, that's this S sub H here, is the sum of every worker that I've assigned to work during a particular hour, given their availability. So if I select a shift, then that goes into the pool of supply, right? And so that's what it's going to allow us to see what the difference is between scheduled and target supply and demand. And so here we have these O and U variables for oversupply and undersupply, and we basically do the same thing we did in the last model, where we say the oversupply is greater than or equal to the amount of demand minus supply, and the undersupply is the reverse. And then every W variable is binary. Every worker is either scheduled or not. All right, so if we now go into the actual code for this, we'll go back here and look at the data. All right, so we have penalties here. So these are penalties per hour of oversupply and undersupply. So in my particular case, I'm just assuming that we are going to penalize undersupply more than oversupply, but that could be different in different use cases. So it's a 1.5 to 5 ratio. And then I've got generated data where I say, when are different workers available? And so, this worker says they're available between 1500 and 1800, and that's an entire shift. So if I schedule them, I'm going to give them the entire shift. And your operations might not match this. So again, this is one of many possible scheduling models. And then I've got required workers. And again, this is just a target this is from the forecast and the targets. So during this block, I want 13. During this other block, I want 32. If we go to our schedule directory, all right, this is in the repo, so you should be able to run it. You can look through the code, and it's basically the same sort of structure as the last model. The important parts are here, where we extend the objective function. So this is where we multiply the penalties by the over and underage amounts. And this is actually where we say what is the over and underage amount, under supply amount for each hour. And that's basically the whole model. So I won't go into it too much, but you can look through the code and see it there. And if we go into this repository, I will push that into a production environment. And part of the reason I want to do this is we have these nice little visuals that we can bring up in the cloud environment, where we can actually see what the input and output looks like visually. So I just ran that input through our cloud environment. And I will go into our apps, and I can see here we have a shift scheduling with OR tools model, which I just ran. And this was the input, which you should recognize. And here we have blocks and availability. And then if I go to the result, I can see I have optimized schedules based on those inputs. All right, so final model we're going to go through is a routing model. And I need to go back into slideshow mode. Oops, that is backward. Here we go. Oh, and if we plot that, this is what we actually get. So here the red is the desired, or essentially demand or targets, and then blue is scheduled after that optimization. And given the assumptions in the data, this is optimal for that particular instance, so you can't really do better than that. All right, finally, we'll go through our routing model, and this one's pretty quick. The basic premise here is, we're trying to minimize drive time and cost, which could be time, it could be distance, it could be some function of those things, it could be earliness, lateness. It really just depends on your business case. And we're trying to have good service levels, right? So missed or late deliveries infuriate drivers. So we've got a bunch of demand. In this case, we're delivering from a warehouse, but these could also be pick up and drop off problems from restaurants or something like that. How do we do this most efficiently and also sort of hit the service targets that users have given us, or we have given our users? The way that we're going to do this, again, using OR tools and their Python interface, we're going to use their routing library, which if you look at it, is really just an API wrapper around their CP SAT solver. So it gives you access to all of those underlying constraint programming primitives. And under the hood, it's constraint programming, satisfiability, local search. It's interesting implementation, and you can find information about how it's implemented in these papers that are linked in the slides. All right, so briefly, our routing speedrun. This is what our data is going to look like. So we've got vehicles. We're going to use a centralized depot here. There's a location that they all start and end at, and they all have different vehicle. They all have the same vehicle capacities. Again, we're just doing carrot delivery here, so that makes sense. We've got a bunch of stops to service. They take different amounts of carrots. And we've got 8 vehicles, and they're all identical. And that might not be the case in your particular use case, but that is here. If we look at the model, all I've done here is just adapt an OR tools example, which is their VRP capacity example, directly into the structure that we have. And so this code is all just ripped right out of there, just using our particular input structure. And what it does is essentially it has these callbacks, which update finite domain variables inside of the search. So as the engine makes decisions, it will use these callbacks to trigger changes between them. And so that's how we deal with things like capacity. This is essentially a capacity constraint. It's done through callback mechanisms. And it's the same with distance. So there's a distance callback, which when it ties two things together, go from A to B, it calls this callback and says, how far away are they? Or how long does it take to get from one to another? And so that's basically the model. And everything else is just, calling the standard OR tool stuff. All right, so if we run this, again, I want to run this in the cloud environment so that I'm going to push it so that I get a nice visual. Now it's pushed, and I'm going to run it and wait for the output. That should take about 10 seconds. I think that's what I put as the default. And while that is running, we'll just go over here and go back into the cloud environment and look at our apps, delivery routing, OR tools, runs. And here I can see this was the input, and so this JSON should look familiar. And here are the optimized routes. All right, so back into slideshow mode. So in summary, forecasting, scheduling, and routing are sort of the three starter models that you need to operate in on-demand delivery. There's a lot of other models, but if you're going to do this, this is really the three core ones. They're sort of like the French mother sauces to logistics. Optimization underlies many or most decision models. If you are using a forecasting library or a routing library or really anything, optimization is under the hood there, and you can just access it directly through tools like OR tools. There's other tools you can do that with too. Many have Python interfaces, so it's worth exploring these and understanding that universe. And if you don't know where to start, you can just take that repository, and that's a starting point where you can at least get up and going with. I also included some exercises that I thought were interesting. So if you really want to go deep here, you can use the same input-output data with a different forecasting tool, like Profit. Uber, I think, released one called Orbit recently. There's also Ceramax and things like that. So it's interesting to compare these. One size does not fit all for forecasting. Another good exercise would be to change the scheduling model to use OR tools' APIs instead of a mixed integer program and just sort of see how that works and what it does. And then I'd suggest also trying a different vehicle routing solver. There's a bunch of them out there. You could try the one from NextMove, which is called NextRoute. You could formulate a MIP. If you're interested, reach out to me. I can send some resources on that. And that's all I have. So thank you so much for your time and attention. And I'll take any questions you have.
Great, thank you so much, Ryan. That was fascinating. So we don't see any questions in the Q&A, but there are some comments. And I guess the first one is you answered that lab one. Yes. Quantile, why not quantile?
Yeah, that's an interesting question. So I think you could use quantile regression in this context. Obviously, that would make the model a little more challenging. But I don't think there's any reason you can't use quantile regression here, and that would be a sensible thing to do.
Great. Thank you. We have the next comment is, can you explain the Fourier features? They are monthly or weekly ? I refer to the frequencies.
I'm not entirely I think this question goes a little bit over my head. But I think what it's asking is to explain the feature. Oh, yeah, okay, I understand, I think. So if I go backward a little bit, we had these features that were here. Okay, so the offset is given the data, just what is the starting point, right? So if you had a line that was just starting at 0 and it had a y value of 100, that would be 100, right? Daily trend, if we look at this, we can see that it's sort of increasing over time, and so that would account for that. If I just stuck a straight line on here, that would really be daily trend. And then there was solar cycle seasonality. I'll refer you to the Rob Vanderby paper a little bit more about that. If you look in the Python code, you'll see some weird stuff involving sines and cosines, and that's what the solar cycle trend was. That really is there for when it's warm out, people behave differently. Is really why that's there. But we could also use things like months, or for instance, school seasons might be really applicable in something like meal delivery if you're in a college town. So it kind of just depends. And then the last ones were weekly. And I can reach out if you want to reach out to me. I can send some more information on some of this stuff. But yeah, if you look, what you'll see here is we have a better split out by day, and there's a certain amount of the variance that is explained by it being a Monday versus a Tuesday versus a Wednesday. And so I think those were all the different parts that were included in here. You'll see a lot of different features sort of make sense in different scenarios in on-demand logistics, depending on the business model and how they operate.